Hello there and welcome back. So today we are going to tackle the kernel loading and elf support. So without further ado, let's get right to it. As you might have noticed, I have moved the code around a bit. I've moved the appropriate functions to different submodules to group them. And I've also did some refactoring on the load file, or the config file loading, to have a function that takes a file name that loads it in a generic manner, and that basically makes our work easy for today. So we want to load the kernel, so let's get straight to it. So the kernel file will be just file system load file, and we know that we have our kernel path under bootloader config.kernel, I think. Yep, that should be it. And of course, this returns an error, so let's catch that, and let's just pick this from here, and do something like this, kernel file, and here we can do bootloader config kernel. There we go. That should be fine. So now that we have our kernel file, we will want to actually load the executable. So for that, we are going to do, so I guess we could set this as const. There's no need to make it a variable for now. So I don't know what I'll call this. I don't know what shape this will take, but I'll just call it kernel for now. And I want to create a new module that I'll call kernel loader. And in that I'll create a function that I will call load executable, for example. And this function will take a slice of bytes, which is basically kernel file .get contents. So to get into more details here, the load file function returns a file buffer struct, and this file buffer struct has the actual buffer, which is a slice of bytes. The buffer we allocate is page aligned and has a size of an integer number of pages, whereas size here is the actual size of the content of the file that we have loaded. So that's why I have this function here called get contents that basically just returns a new slice from that buffer to the actual size of the file contents. That's pretty much all there is to it. Right, so this here does that. I guess this will return some sort of error, so let's handle those. I guess I'll just go ahead and copy these from here, and could not load kernel executable. Something like this, and that should be pretty okay. So I think I'll also add something like this, just to avoid this being unused, and then I'll go ahead and import kernel loader, which will be import of kernel not leader loader sig, and now we just need to create this file. So kernel loader.sig. There we go. So I guess we'll start by importing stud, since we'll going to need it for pretty much everything. I'll probably just import UEFI because we might need it from stud, and yeah, we'll see what we need afterwards. So I'll create a logger. So this would be stud log.scoped, and I'll call this kernel loader. And that should be it. So now I could create my function, what do they call that? Load executable, I think. And we said that it takes kernel file, which is a const slice of bytes of U8. And this, of course, would return a bootloader error. And otherwise, it should return something else. So if I have to, so let me just go ahead and take a look at what we did for the other BIOS, or for the BIOS bootloader. So I think it's under main, and I think we have should be called load executable, kernel executable. Yeah. So this one here returns a kernel info, and kernel info is what? It's the entry point and the segment mappings. Okay, so I guess we could do the same thing pretty much. So I'll just create kernel info struct here. Let me just do this and go ahead and create. So kernel info is a struct, and for now I'll just leave it at that, I think. Of course, we need to import the bootloader error. So this is import called that file errors.zig, and that should be it. All right. So what we want to do here is pretty much what we did for the main. So we want to check what type of executable we have, and if it's an elf file, we'll call a function to load elfs. Otherwise, for now, we'll just return an error that says that the format is invalid. So let's do that. So I guess we want to do kernel signature, and this would be kernel file, and we just want to take the first 4 bytes from that slice, and then we'll go ahead and do a stdmem equal to compare them. So it's U8 as the type, it's kernel signature, and what we want to compare it to is, so instead of having to redeclare all the elf structs and enums, I'm just going to go ahead and use the ones that are declared in the Zig standard library. So I'll go ahead and import those. It's actually pretty cool because it saves quite a bit of time. So std elf is what it is. So elf dot, I think it's called magic. Yeah, there we go. So if that is equal to that, then I guess we could log info kernel matched elf signature, for example. And of course we do this, and here we can just return. And I guess I could create a function that I'll call load elf that basically just takes a kernel file and returns an error or a kernel info. So here I just want to return bootloader error dot invalid kernel. I guess I could do unhandled kernel executable error. Just yank that, put that in there, and that should be fine. Right, so now we just need to create our function. So load elf takes kernel file as a slice of const bytes, and returns, of course, bootloader error or kernel info. There we go. So I guess we need the elf header now that we know that this is an elf. So so const elf header, and this I think will be, or I guess this would be a pointer to elf.elf64 header, header, I think. Let's take a look at that and see. I think that's what we want. Right, so this one here will be, so it's just cast that to, so elf header, whoops, needs a few more things. So cast pointer, or pointer cast, and of course we'll also need to align cast that, and probably even const cast it, since, actually we don't need to const cast it, we can just go ahead and declare this as a const pointer, or a pointer to const. Right, so, and we pass it kernel file dot pointer. I think there is a bit more elegant way to go about this, but I think there is something under std_mem that takes value, bytes as value. So given a pointer to an array of bytes, returns a pointer to a value of specific type. Yeah, I think we should probably use that. So let's rewrite this. Const e header is std_mem bytes as value. So it takes a comp time, so that would be elf header, and bytes would be so kernel file, and we'll need to slice it exactly to the size of a elf header, I think, unless it does it automatically, but yeah, it does not. So let's slice it using size of. So elf header. There we go. So that should be a bit more, a bit better than just doing raw token casts. Right, so now that we have our header, we need to do some checks to see if we actually have a valid kernel executable. So we just want to support elf64 for now, so we are totally going to disregard elf32, and to do that we are going to need to check, so if eHeader dot, so hold on. Okay, so I just need to tell it that this is a pointer to elf header, so that I can get some autocomplete. There we go. So this one e-indent is an array, 16-byte array, 16, right? Yeah, which is all the identification fields. So let's start by checking the class, and I think that's under elf ei class. There we go. So if that is not equal to elf dot, so I think it's elf class 64. Yeah. So here we can just go ahead and return a bootloader error, and I'll call it invalid kernel executable, just to keep it generic. And also I'll go ahead and put a an error message. Unsupported class, and I'll just write the class in there. And the class would be eHeader, eIndent, ident, sorry, and elf AI class. There we go. That should be fine. Right, so and then I guess we could just basically just do a few copy pastes of this and check different things. I guess the next thing we need to check is the data, which is basically, I guess we don't have it here, but we should have something like, so LSB, yeah, there we go. So we want the ELF file to be in least significant byte format. Otherwise, unsupported in DNS, and this here will be, oops, this here will be ELF or AI data. And here we can just copy this again, and let's try to do, I guess that should be pretty much it for the item. So now we need to check the machine, and machine is actually a an enum, so we can just do x86-64 machine, and here we can do s, and we can do tag name of eHeader.machine. Yep. So that's the thing, and now we can check the type. We want this to be an executable, so I think we have a type exec in this executable type enum. We can do that, and here we are going to need to change this to e_type. There we go. So I think that if we have all these fulfilled, we can go ahead and start loading our file. So first thing I'll do is I'll create a kernel info struct, which will be of type, of course, kernel info. And this will be just an empty struct for now. Or I guess since we already know that we'll have the entry point, we could just create an entry point in there. So this will have entry point being equal to eHeader dot, I think it should be called something like entry, yeah. There we go. Right, so now we need to basically load the rest of the file. So to do that, I will just open up the main.c file. And we will try to basically see what we did here. So I did pretty much the same things as this, checked all the things that we wanted here, and here we are going to start looping over the program headers. So let's start doing that. So I guess we could just create a const. I'll call it p headers, and this will be so I'll stud.mem. I guess there's the same thing as slice. Yeah. So this is fairly interesting. So basically what this does is it just does the classic as pointer cast thing that we usually do, but it also takes a slice of that by taking the length of the bytes and dividing it by the size of one item. So you get an actual slice of the items, and you can just loop over it without having to use a sort of index or something like that. So let's do this. This would be elf, so elf64, and I think it's p header. There we go. And here we need to pass it. So this would be kernel file, and we need to slice it to exactly where we we need to slice it to exactly where we want to take the program headers. So for that, we are going to take the program header offset. Oops, that's missing an E there. And we are going to go all the way to E header. So E program header offset plus E header dot program header number multiplied by E header dot program header so entry size. So basically we are multiplying the number of program headers by the size of one entry to know how many bytes we should have to work with. Right, so that basically gives us a slice of program headers, and now we could basically just work with these. So I think we are just going to so for program headers, and we capture the header. So LSP is having a bit of trouble, so I need to annotate the types here. So this would be a slice of elf64 program headers. There we go. Right, so here for every program header, what we need to do, so first of all, we check if it has the correct type, which is basically what we are doing here. If it's not type load, we just continue. Right, so if p header dot p type is equal, or rather is different to okay, so it's not an enum this. Okay, it's not an enum. So it should be something like load, pt load. Yeah, that looks pretty good. So if it's not pt load, we just continue. Otherwise, we will want to so const file size is program header file size, and const mem size is program header dot mem size. There we go. So now we have our the sizes of our program header or our segment. We need to check that the size is not too big. So if mem size is over, I guess I could create this 64 megs. Then we probably just log error. What's a good error here? Kernel too large. And probably even put in the size so that we know. And this would be mem size. I think that would be good. Yeah. So let me just quickly go ahead and create this. So function. So mb takes a value which is a u size, or it's a comp time int, and this will return a comp time int. There we go. So this returns a value times 124 times 124. Oops, there we go. Right. So is there a way to make this inline? There we go. Cool. So now that we know that, hold on, I forgot something. So here we need to basically bail out. So bootloader error dot kernel to large error. Right. And we could do this. There we go. So that looks pretty good. So now that we have, so we know that we need to load this segment, we need to allocate some memory for that. So const, we need to basically know how many pages we want to allocate. So pages to alloc. And this would be, so we just need to divide the size, the mem size, by a page size, while of course aligning them forward so that we take an integer number of pages, right? So I guess we could do, so there's something under stud mem for align, I think it's align forward, round up an address. Yeah, that looks pretty good. So use64 is the type. Our value is mem size, and our alignment is a page size. And then we divide that by a page size, of course. Right, so we have our pages to alloc. So we are just going to have to call our UEFI boot service to allocate the pages. For that, I think we just need a const status, which will be globals. So I've created this globals module here that basically has just the systable and boot services that get initialized on startup. So that's what this basically does. Right, so globals, I'll need to import that, of course. So const globals is, oops, let's see, import, and I think it's called globals.zig. There we go. Right, so globals.bootservices.allocate pages, and this takes what? It takes the allocation type. I think we just do allocate any pages. The memory type is loader data, which is what we use, what we used till now. Then pages to alloc is the number of pages, and then we need to pass it a pointer to a buffer. So call that load buffer. So now we just need to create this load buffer here. So load buffer. I guess this one is a multi-item pointer that has a page alignment, and that has of type U8, of course. And I'll just initialize that to undefined. There we go. Right, so I guess we just need to handle the status issue that we might have. So I don't really want to do that, but let me just go ahead and copy it from somewhere. Where would we have this? I think in memmap, or rather no, in file system fs. There you go. So in fs we should have created pages, so we can just go ahead and yank this over to here. Right, and I guess I could just do this for now. So this is pages to allocate. I guess we can just rename this to pages to allocate. And then path, we don't really care about that. There you go. Right. Yeah, this is bad. This is something to be fixed. So let me just put a to do. Right, so I guess we could do memory or page location error. And we can just go ahead and put that somewhere here. Oops. There we go. That should be fine. And actually, let me just go ahead and do page location error here and get rid of this. Yeah, that looks pretty good. So let me just clean this up a bit and we can go back here. Right, so now that we have our page allocated, we can basically go ahead and copy our memory over. So we are just going to memcopy our memory from, so it takes a destination and then a source. So the destination would be load buffer, and we need to slice it to the correct size. So that would be load buffer from 0 to file size, I think. Yeah, and then the source buffer will be so kernel file, and we'll slice that from so p header dot offset to p header dot offset plus p header dot size or dot file size, or just file size. Yeah, I think that looks pretty good. Yeah, that's okay. Another way to do this would be to basically slice it twice. So do a first slice here that basically goes to from p offset to the end, and then do another slice that goes from 0 to file size within that first slice that we did, which is, I guess, a bit more readable or a bit easier to understand, but I'll just stick with this one. Since it's not that complicated. So const, I guess now we need to compute the amount of BSS bytes or zero initialized bytes that we need to fill in. So BSS size is basically just the difference between mem size and file size. And of course, so if we have, first of all, if BSS size is larger than 0, then we basically go ahead and do a memset. Memset takes a destination and the element that we want to set. So the destination would be load buffer, and we are going to start the setting from file size. So file size, and then we're gonna add mem size basically. So we are going to initialize everything between file size and mem size to 0. There we go. So that's our BSS taken care of. Right, so now that we have loaded our kernel segment, I guess we could just add it to our kernel info and we can move on then. So kernel info dot, I guess I'll create segment mapping, and this will have a physical address, which we will take from p header dot p address, and then it'll have kernel info dot segment mapping dot v address, of course, which is p header dot v adder, and it'll have kernel info dot segment mapping dot I guess length or size. I'll call it length. This one is mem size. So I guess we can go ahead and create these in our kernel info. So this would be segment mapping, and this will be of type just call it mapping info. So const mapping info is a struct that has a p address, and actually I want to use some of the language niceties to create an address type or an address union that has a backend enum, which is so either p address, or let's call it physical, and this would be just a U64, or virtual, this would just be U64 also. There we go. So now this p address I'll just set as type address, and v address I'll also set as type address. And of course we'll have length, which would be just a U64, I think. There we go. And here I'll just add this comma here for nicer formatting. Right, so let's go down and see what we have. So I guess this one here will need to change to be so physical, or rather, this physical is p header dot or oops p address. There we go. And this one here will need to change to be so vert is p header dot v address. There we go. So this one is a U64, and this one is also a U64, so that's pretty cool. Right, so now that we have these, I guess we could add a log or a debug log just to add something like so loaded program segment to 0x, something like this, and here we'll put I guess the address where we loaded the thing, so load buffer. Yeah, that should make for a great little log there. And here, once we are done with this, we should also go ahead and do debug. And actually, hold on, so let me just break once we do this. So here I'll just write loaded or finished loading program segments. Yeah. And here we'll just do this, and we move. So here I want to do something that's a bit different from what we did for the BIOS bootloader. So for the BIOS bootloader, we basically just stop where we are now, and we just return the kernel info. But for UEFI bootloader, since we have quite a few niceties from the language and also from a standard library that's pretty cool, pretty usable, we should probably try to do a bit more. And what I want to do is, so here if I go to our, so this is the kernel stub that we are going to try to load. In the linker script, I've added these two things here. So these are two symbols. One is FB, frame buffer, and one is boot info. So what I want to do is I want to load the elf, read what values these two symbols have, and then map the frame buffer and the boot info section or the boot info struct to those addresses so that the kernel can choose where to have those instead of so what we did in BIOS is we are pretty much forcing the kernel to have them at a certain address. We have frame buffer is that beef and boot info is cafe babe, which are the values that I've set for those two right here. So we are going to try to read those. But first of all, we need to read the section names so that we can filter out symtab. To do that, we are going to need to go to the very last section, which is pretty much always section header string table or sh stir tab. And in this section here, we are going to find all these names. And this section here is where the field section header dot. So if we basically take, let's take section headers. So as headers, and we'll do stud.mem.bytes as slice and elf64 underscore as header, and we are going to pass it kernel file. So e header dot section header dot e section header offset and e header dot e section header offset plus e header dot e I believe it's section header number, so pretty much the same thing as the program headers. E header dot e underscore section header entry size is what we are going to do. Of course, this needs to be const, and this one doesn't know. So if we go to a section header, we have this section header name, which is basically an index into that section header string table array. And the way we take the name is we find this section header string table, and then we take that index, we split or we slice, well, it's not really a slice, it's a zero terminated string starting at that offset. And we just read that, and that would be our name. So let's actually get working on that. So we have our section headers here, and we want to check that. First of all, let's check that we have a section header string table, because I'm pretty sure that it's not something that is ensured to exist. So it's section header stir tab. I'll need to check elf header. Elf header. So this is what we want. So section header string index with an n. So string index. Yeah. So if this one is larger than, or it should be smaller than, so e header dot e section header number. So if it exists, if we have an ID for that section that's less than the total number of sections, we can go ahead and try to read from it. So here we have all the section headers in as headers, and we are going to take section header string table section header, and this would be the very last section header. So as headers at offset e header e section header string index. Right. So we have our section header here, And now what we are going to do is, actually before we do anything, let's first set ourselves a little message. Let's do something like section header tab or stir tab found at offset. Let's do something like this, and here we are going to just write section header string tab section header, which is the section offset of that section header. Did I miss? Oh yeah, of course. So this one would need to be section header. Right, so now that we have those, we need to create a const. So this is the section header for that section, for the section header string table. So now we need to actually create the slice, which is the section header string table. So section header string table is so kernel file, and we'll slice it from that so string table section header dot I guess it's section header offset offset, and it goes all the way to I guess it goes all the way to section header string table s header dot sh offset plus sh string table s header dot sh size, I believe. I'm really gonna need to fix the LSP on this one. So it's really struggling with these bite-sized slices. So for now, I'll just I guess do something like so elf 64 section header, I guess. Yeah, there we go. So this one here is a const-u8 slice, so that's fine. And now that we have this, we are going to need to find sections that have the name sim table, and we are also going to need to find a section that has the name string table, so that we can find the name of every symbol. So let's try to do that. So I'll create a actually I'll just go ahead and do for section headers capture section header, and here we are going to const so section name. This will be basically section header string table at starting at offset section header name, yeah, and go into basically the next 0. So we might want to find the 0 before slicing this, or we could basically just slice it and not care. So the only issue is that if we slice it and not care, if we do something like debug found section with type, I guess we could do that as decimal, and name s. So if we do something like this, since we are going to pass zig, so this would be section header dot sh type and section header dot, or rather the section name. So if we do something like this, since zig will take the slice length, which is basically the full length of section header string table starting from the name. it will print the whole thing, but we know that we only care about this up to the first null character. We could add a check or a search for the first null character here, if we wanted to do that. I think there's something instead mem span, maybe? Yeah, so we don't really care about that. So we move. We are going to have weird formatting for the debug logs, but we don't really care about that. And it's not really worth to introduce the performance penalty to look for the 0, because we're not going to use it for anything. So here we are going to need to check that we found the name or the section that we are looking for by comparing the name. So U8, we are going to take section name. So we want to compare section name sliced to something with the string symtab, which is the name of this section here. And to do that, I'm just going to take from 0 to 7, because I know that these are 7 characters. So we just need to compare that. So that's why I didn't bother to slice section name to its end character, since I don't really care. So if this is found, I guess we need to set some sort of variable. So I'll create something like symtab section header optional, and I'll set that to section header. And then I think I'll do pretty much the same thing for this other section that's called stir tab, which contains the symbol names or any other string. And here I'll pretty much do the same thing. And I'll just go here and create var symtab section header optional, which is an optional elf 64 as header, initialized to null, and I'll do pretty much the same thing here, but this is a stir tab. Right, so now that we have found our 2 sections, or we think we have found our 2 sections, we are going to need to check that we did. So symtab string header optional, capture that as symtab section header, and in here we are going to check for stir tab section header optional and capture that in stir tab section header. And here we are going to, I guess we can do log debug and do found symtab and stir tab. That's something that's good to know. Right, so now that we have both of these, what we need to do is, so the same way we did here, we need to create a slice that's basically all the strings. So const stir tab is kernel file, and we'll slice that from so stir tab section header dot offset to stir tab section header dot offset plus stir tab section header dot size, I believe. There we go. So now that we have our byte slice for all that contains all the strings, we can go ahead and start looping the symbols, I think. So let's create our symtable slice. So symtab, which is, I guess we'll use bytes as slice again. And this will be elf 64 sim. Is there a sim? Yes, there is a sim. And to which we are going to pass kernel file, not info file, and we are going to slice that from so sim tab section header. So offset all the way to symtab section header dot offset plus symtab section header dot size. There we go. Forgot this here, but I think we should be good. So this one I'll just type hint it because the LSP is struggling. So this will be a slice of elf sim. So this will not compile because we are stripping away the align one that comes with this, because this kernel file here has an alignment of 1 since it's a just a byte slice. But we could declare it everywhere, but I don't feel like it. I know that the compiler, the Z compiler, can actually compile this even without the type hint. It's just that the LSP ZLS struggles a bit with return types that look something like this. So any comp time, return type, computation, ZLS will struggle. So it needs a bit of help with that. Right, so now that we have our symbol table and our string table, we could basically just do the same again. So symtab, and I guess we could do symbol. Yeah, we could do symbol. Let's just split it out. Symbol, and for every symbol, what we want to do is we want to look up its name. So I guess I'll create something called symbol name, and this will be stir tab, and we will slice it at symbol dot name, I think it's called, yeah. So pretty much it's fairly similar to what we did here for other section names. Right, so we have the symbol name, so now we need to basically check if the symbol name is one that we are interested in. And to do that, I'll just do stud mem equal, of course we are comparing U8s, and I guess we could do symbol name. So what's the first one? I guess the first one will be, let's go with frame buffer. So frame buffer, and of course I need to slice this with the correct length. So this goes from 0 to 2. And if we find this, I guess we could first of all just do a debug log. Found frame buffer symbol with value 0x, something like this, and we do symbol dot value. It's a U64, so that should be fine. And of course here we need to kernel info dot frame buffer binding, I'll call it, is equal to symbol dot st value. And actually I'll use the address thing we've created. So symbol dot value. Yep, looks pretty good. So now I just need to copy these a few times. So there are 3 values that I want or that I'm interested in. The first one is the frame buffer. The second one is the boot info struct. This one has 8. Boot info with symbol, of course here, boot info binding. And the third one is the environment config. that we want to pass our kernel. So that looks okay, and this would be env binding. And of course here we return the kernel info. So I guess we just need to go up here and add, so if maybe I should group these, so const bindings struct, and I'll do frame buffer, which would be an address, and which is an address also, and boot info, which is an address too. Bindings is of type address bindings. There we go, and also I'll just do so this one here will be fizz, or rather .fizz 0, and I'll just init all of these. So vert is 0, that is 0, and here instead of doing this, I could just do that, and here is so I'll probably make all these optional, and I'll just do this, because we might or might not have them. Right, so this, I guess we could also just do that. And that will save us a bit of headache. So here I want to add address bindings and frame buffer. So address address bindings, boot info, and address bindings, env. Yep. Right. Actually, let me just check something. Yeah, that looks pretty good. That looks pretty good to me. So I guess now I can just go ahead and remove all the type hints that I've added pretty much everywhere, at least for the results of by the slice. And let's try to build this. And there you have it, first time build. So let's try to run this and see what issues we have. Oh, it actually works first time. That's a surprise. Right, so here let's go ahead and take a look at our debug logs here. So kernel matched alpha signature, that's expected. So allocate one page for the segment contents, that should be okay. The segment was loaded to this address here, and we only had one. We have string headers, stir tab at offset 4960, that's fine. I want to trust you on that. And then we have, right, so this is the issue that I've talked about. So there is a 0 here between the B and the dot, but since Zig is pretty much reading the full length of the slice and printing all of that, it is ignoring the 0 because it's not printing C style characters, it's printing the actual slice. But we know that this section here has name symtab. This one here has name text, this one is BSS, this one is comment, etc., etc. And here, this one is symtab, and this one is stirtab. And I guess we found sim and stirtab, and we did find the correct values for our symbols. So that's pretty much what we set out to do. So 2 boxes checked today. We've loaded the kernel and we've added Elf support. I think we can call it a day. As always, if you like this type of content, hit like, subscribe, and share the word. And until next time, see ya. Bye.